Yo, what's up, guys? Welcome back. Episode 150 today. Halfway to 200. Let's go. Halfway to 200, baby. But yeah, I'm probably gonna jump through a few problems today. I'm not sure what we're gonna do. Probably go through top 100 most liked or something, but pretty excited for that. So let's get into it. Let's see what our problem of the day is today. Don't know what it could be, but we got a hard problem today. Some of K mirror numbers. Actually, I remember seeing this at the end of the day when I jumped back on. It is a bit manipulation, or it looks like a bit manipulation problem. So I don't know if we're gonna do this because I hate bit manipulation, enumeration, math. We're gonna leave this for now, I think. Last question. Let's skip it. I'm not gonna do this one today. I'm gonna do something different. Let's take a look at our study plan. Kind of want to reinforce those topics first. I feel like that's definitely the most important thing. I want to do something I haven't done. Maybe we can take a look at jump game. Let's warm up with like a problem. Maybe something straightforward. Maybe we can invert a binary tree or something just to get straight up. Given the root of a binary tree, invert the tree and return its root. Okay. So let's jump into Python. What do we want to look at here? Let's take a look. So we are returning a node here. So I think what we're going to have to do here is we're going to have to create a tree node here. So let's take a look here. Let's jump up a drawing here. Okay, so what are we going to do here? We got to invert the binary tree. So we got 4 at first, then we got 2 and 7, 7, 2, 1, 3. So we're just inverting it, flipping the numbers. Trying to think what is the best way to do this. Maybe we can do this in place, being we start off 1 second, sorry. Oh my gosh, dude, what is going on here? So I'm thinking maybe we could start off. Well, I was thinking really creating a whole new tree node, and I think you can probably create a whole new tree node. Like we would go here and we would have looped through this tree. We could make a whole new tree node, but I just don't think that's the best way to do it. I'm probably thinking we could just invert in place. So, you know, as we loop through this tree. Oh, whoops. As we loop through this, right? We can keep track of. We can have 2 pointers, right? Keep track of 1 pointer going left, right? And then another pointer going right. And then, I guess I'm just using different colors. You know, we can make that swap here, right? Because really, as we go left, when we go left, we're swapping it with right. When we go left, we're swapping it with right. So it's like, you know, the opposite. I mean, we're really just inverting the tree. So, so what I'm thinking here is we go. Well, I guess we could probably just pass in def DFS, pass in our node here. Come down here and do, well, if not node, we can just return. We call our function here DFS with our root, and we can can loop through this, right? So we pass in our DFS root. Really what we want to do is we just want to return the root. So I guess we would just return root here, loop through this. What we would do here is we probably want to return. In Python, we can easily swap here. So we can go, well, actually, maybe we can do, well, no dot left, no dot right is equal to no dot right, no dot left. Can you do this though? I'm not really 100% sure. It's on my head. That's what I'm trying to think. Can we do that though? No dot left, no dot right. I feel like here is equal to DFS. No dot right. DFS, no dot left. It's the empty function. What are we returning here? 231, output 2. Return root. DFS root. Passing in our node. This being our base case. Our no dot left, no dot right is equal to DFS, no dot right. DFS, no dot left. I feel like this seems like it should be good. I don't know. Seems like this. We're not returning. That's why. How did I miss that, dude? There we go. Okay. That's what I thought. So we assign our node dot left and our node dot right, and we swap it with our DFS node dot right and our DFS node dot left, which means we go into the next one. Typical recursion here. If not node, we would swap. Call it again. Return back up our call stack. So I guess we can kind of visualize this just to be sure what we're doing here. We would have 4, 2. I just like to visualize these things sometimes just to kind of have a good idea. Kind of helps me when I come back to these problems. 1, 3, 6, 9. Okay, so we're given these. So really what we do is we start at our root, right? We assign our node dot left and our node dot right to be DFS, node dot right, node dot left, right? So we look at our node dot left, look at our node dot right. We swap these, really. That's what we're doing. But really this recursive function is going to keep calling it, right? So we will go all the way through our recursive function, come here. When this is null, right? Our base case is null. We would return and come back, right? Really, what would we do here? Well, we do node dot left, node dot right is equal to DFS, node dot right, node dot left. So really, I think we'd swap down here. We'd come back, but really they're both null. So we'd come back here, return to this one. We'd swap these ones, come back up, swap these ones, and then come back up to our root function, return our node. Back up to our recursive function. So I think this should pass. I mean, nice. Maybe just to kind of warm up, let's do it the iterative way, right? So if we were to do it the iterative way, we'd want to define our stack. We would want to append our root to the stack. We would go while stack. We'd want to node is equal to stack.pop. Okay. We would probably want to do what is a stack last in first out. So it's been a while since I've done a iterative stack approach. Let me think here. Last in first out. Think of it like a probably want to think of it like some books, right? Like some of these basic concepts even just get to me sometimes. Like think about it like a book, last in first out. So you know we'd be stacking our books, last in first out, right? Okay, so we pop our node here from the stack. What do we want to do when we pop our node? Well, we probably want to get our node.left and our node.right. Right, we probably want to swap them. So let's do our node.left and our node.right is equal to node.right, node.left. And then we'd probably want to check, well, if node.left stack.append node.left, right? If node.right stack.append node.right, right? Then we'd probably just return our root. I would think this should probably work. Object has no attribute right. Maybe we can do if not node. We would return right here. Maybe that'll fix it. Can I select variable node where it's not associated with value? Whoops, meant root. Let's run this. Oh. If not root, maybe we just return none. There we go. See if this submits. Okay, sweet. Good to feel out the iterative approach again too. I feel like that's probably an important thing as well. Just kind of feeling out both ways, you know, having a good understanding. Okay. What do we want to do here? We were going to finish this problem the other day, actually, when my computer crashed, so maybe we should probably finish it. What were we doing here? We have to kind of look back at this problem. So we're on 79 word search. Temp is equal to word. We print out temp, rows, length board, col is equal to length board 0. We have our directions array here. I guess we're running some sort of DFS here, right? If the let's actually look at the problem again. Given m times n grid characters board and a string word. We have to return true if the word exists in the grid. A, B, C, C, E, D. The word can be extracted from letters sequentially adjacent to cells, or adjacent cells are horizontally and vertically neighboring. The same letter may not be used more than once. Okay, so what do we do here? Right, so we enter our function. Temp is equal to word 0. So we're assigning a first character here, taking a look at it. Making our rows and our columns. We have our directions array here that goes up, down, right, and left. And we have a simple iterating over our rows and our columns. We're checking, okay, well, if the board row col is equal to temp, so if it's a starting character, which is what we want to look at, we run our DFS from here and then we return true. Okay, so then we have our base case here. If the length of the word is equal to index. Now, what is index in this case? 0. Okay, so if we've added, I understand what we're doing here. If we've got the length of the word, the length of the word here would be 1, 2, 3, 4, 5, 6. So I believe this would be the length of the word minus 1 is equal to index, right? Because we'd be going by 0. So yeah. What do we check? We check the bounds. I remember we had an issue with these bounds here. We add to visited. This is where we do the recursive part, where we loop through directions, make a new row. And then we want to check, okay, we check the bounds, right? If it returns true, then we know visited is fine, so we can remove that. We start here. We add visited, we loop through, get our new row, new column. If DFS new row, new column returns true. Oh, sorry, if this returns true, right? And the only way it can return true is we get to our base case. Then we would return true. But if it's false, then we'd instantly return false from this. Okay. And if we return false, we would just keep going through. But I think we had an issue here. So if right is less than 0 or right is greater than or equal to rows, C is less than 0 or C is greater than or equal to, because we have and board. Or we could, I think this would just all be ors. I don't know. Okay, well, we've got something fucked up here. Because if any of these are false, then we know it's false. But we're getting a expected false, but we're outputting true here. Somehow this is coming back, but that was the issue. I'm not sure why this is not coming back. I'm curious. What is my bug here? Purchase almost correct Nazi structure, use defensive backtracking. Yeah. Your base case is in the wrong place in the DFS function. You're checking if the length of word minus 1 is equal to index, return true, before you even check whether the current cell matches word index. Okay. So that is true. This does need to be moved down here. We need to be checking the bounds first. And then we'd want to return that as true. Wow, so that was our issue. We had to switch everything to ors and just put this below it. Let's see if this submits. Okay, sweet. That's submitted. Interesting problem. I want to take a look at my past submissions here. We did do this on December 22nd. How did we do this? The same way. We had an isValid function. We use an iterative stack approach, which is the same thing as my recursive DFS. So, okay. How did we do it in April? Same thing. Looks like we did recursive DFS as well. Interesting. Same way. Instead, we check the bounds here. Okay. Okay. Let's take a look at a problem that I haven't done today, because I always like to do a problem every day that I haven't done. Let's take a look. I have not done jump game. So let's take a look at that. One second. Sorry, I just got to text someone. Okay. Okay, let's take a look at this. Jump game 55. You give it an integer array nums. You initially position the array's first index, and each element in the array represents a maximum jump length at that position. Return true if you can reach the last index, or false otherwise. This is in... this is a greedy problem. How do we want to think about this? 2, 3, 1, 1, 4. Jump one step from index 0 to 1. Index 0 goes to 1. Then 3 steps to the last index. We're given an integer nums. Given an integer array nums, you're initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. So what, you can jump from 0 to 1, then jump from 2 to 3, then 3 to the last index? Is that how it works? You arrive at index 3, 3, 3. No matter what, its maximum jump length is 0, which makes it impossible to reach the last index. I feel like this is kind of a shitty explanation. Problem a little. I feel like it's kind of a shitty explanation. You're given a list of integers nums where nums I is equal to max steps you can take forward from I. Turn true if you can reach the last index, otherwise false. So we just keep looping through. So at index 0 to 2 means you can jump from index, means you can jump to index 1 or 2. Oh. 2 means you can jump to index 1 or 2 from index 1. 3 means you can jump to index 2, 3, or 4. You can reach the last index, return true. Okay. So... which language you were doing, bro? I'm doing it in Python, dude. Python's the way to go, bro. Satyam, I'm using Python, bro. What about you, man? You usually do these problems with Python? So I'm trying to think here. We have our array here. 2, 3. Whoops. 2, 3, 1, 1, 4. So we start at index 0. We check our number, right? When we check our number, then we know where we can go to in our array, right? So we can either go to this number, or we can go to this number, right? And in this case, when we go to this number, we can go 1, 2, 3 steps, make it to the last index in our array. So I feel like this is probably going to be probably some sort of backtracking problem, I would feel like. Yeah, it is. Dynamic programming. Same thing. Some sort of recursive function here. So that is my intuition here, is definitely a recursive function. So what I'm thinking here is, how do we want to do this? We probably want to go def backtrack. We want to pass in our nums. We obviously probably need our index too, right? Our base case here to end our loop here would probably be, well, if index is equal to the length of nums minus 1, right? Then we would return true here, right? I know this is a dynamic programming problem. Well, I mean, it says here dynamic programming. And we will implement that. I just kind of want to get the backtracking solution, then I implement the caching to it after. What I'm trying to think here. Maybe. Let's see here. We have our base case here. So if we see that, then we probably want to go, okay, well, we'd want to go. How do we want to do this? Well, maybe we can do some sort of like for loop here. Loop through. See, I don't know here. What I'm thinking here is doing a. I don't know if there's a better way to do this, but like, really the only way I'm kind of thinking about here is we get out. Let's switch color here, actually. We get our index value, right? That being 2. And we can loop through with a 4. Loop through both the values. We go to 2. Oh, sorry, we go to this one, right? And then we go to this one. Okay? Because these are the 2 values we can get to. And then we run our function. I'm going to name it B. We run our function from that index value. I feel like that's definitely more of like a kind of like a brute force sort of method. Would it work? Probably, but I feel like it would be slow as fuck. But I'm not sure here. So I feel like here there must be like some sort of negative numbers or something. Maybe does it really say constraints 1 to the length? There's 0. Okay, so there's no negative numbers. If you're given an array, you initially position at the array's first index, and each element in the array represents your maximum jump length. That position return true if you can reach the last index, or false otherwise. If you can reach the last index, does that mean you can reach this? The last here? Or can you reach more than the last? The last or more than the length of nums minus 1? I'm not sure. Trying to think here. I think what I'm going to do is I'm going to go from here. So we go for I in range. We start from our index. We increase. I think we can step by our nums index. We can go through to the length of nums. Let's see. Let's print our. I think that should work. We started our index, so whatever number we're looking at, we can go up to, well, this was step by 2. We don't want to step by 2. We want to go, we don't want to step by 2 intervals. We want to go through everything, but we want to be limited on where we can go to. So maybe, is there a better way to go about this? I'm not sure. I am not sure. Let's have a look. Is there a way you can... Or can we end here being the numbers index here? I've never tried this. I don't know if this would even work. Let's print our... Oh shit, I'm not even calling this function. Start at index, and we'd stop at numbers index. Can we use this? Through numbers and call backtracking function. This doesn't correctly generate the next jump positions. It's how far you can jump from the index, not the index itself. So they're saying here they do for index plus 1. So they start at the one in front. They take the minimum of the index plus the nums index. Nums index plus 1 through the the length of nums. The colon. Index plus 1. We take the minimum of index the minimum of index. Okay, so we do that. We would call our backtracking function with I guess we don't even need nums in here. Why am I passing it nums? Backtrack I. We probably need if here. If backtrack I, we would return true. Return true. Return false. Yeah. And then we'd want to start our backtracking from our 0th value and return this function because we're looking for a boolean to return. There we go. Will this not return? Might need to add some sort of memorization, I think. Yeah, TLE. Okay. Let's kind of go over this and see what we get here. So we go for I in range index plus 1. Okay, so we're looping from the value in front of it. We start at 0, we loop from here. And we're going to the minimum of index plus nums index, the min of index plus nums index plus 1 to the length of nums. Starting number inclusive. So we take the min, I think, to stay in bounds. I think that's why. We take the min here to stay in bounds. And that's why we're taking the min, right? We start from index plus 1 because we want to start from this value. And then we take the min of the index plus nums index plus 1. Because we want to go from our current index 0 and we plus the actual nums index, right? Which could be this one. So we would go 1, 2, 3. And then we include the 1, 2, 3. Plus 1, and we go through the length of nums. Because if it's greater than the length of nums, then we would index 2 min 6 index 9. Use plus 1 because range is exclusive on the end. So to include the farthest jump index plus nums index, you need to go 1 past it. Okay, so this plus 1 includes the, because when we think about our min function, it's an inclusive, exclusive. So we have to use the plus 1 to go 1 more. So that makes sense. Then all valid next jump. Gaming buddy, what's up, dude? Thank you, bro. Thank you for the support. Thank you for the support, gaming buddy. Really appreciate that, dude. How's your day been, bro? Keep it in bounds. I'm also a computer science student pursuing my bachelor's in AI and machine learning. Nice, dude. That's cool as fuck, bro. What do you go to school, dude? You enjoy it? Yeah, so that's what I thought. This length nums keeps it inside, right? So if we want to add some sort of caching here, we probably want to do minus core dictionary. Sorry, dictionary. I guess we could, just do this. So it keeps the range safely in bounds. It's the farthest jump you can jump to. Okay. So I think here really let's just call this DP. So really to add this, we would have to go, well, if index in DP, we want to return our DP of you know what, buddy? You are my true motivation. I mean, whenever I procrastinate, I used to watch your videos and live it, ignite fire in me to learn and grind, hustle hard till I not got success. I really appreciate that, dude. Thank you. I don't think anyone's really ever told me that. I really appreciate that my videos. I think that's really cool, dude. That my videos motivate you. So thank you for that. That was a really, really kind message. I try really hard to not make any excuses to keep going every day. So thank you, man. That made my day. Thank you for that message. How long have you been watching my videos for? As it, like, when did you start? When did you find my channel? Did you find it like 100 days or 50 days or something? Or how long have you been around? But thank you for that. Thank you for that message, gaming buddy. That was really kind. Thank you for that. I'm really happy that I motivate you and hopefully others. So it's definitely fun. I didn't think I'd make it this far, but you know, every day I just want to keep going and keep learning, and so thank you, bro. Thank you for that. I'm gonna pass no index here. Right, because this is really where our Memo comes in here, right? Checking here. We want to check. Okay, well, what do we want to store inside of here, though? We probably want to store if it's a Boolean, right? I would assume. So we'd probably want to go make this a true. If it's false, probably want to come down here and do DP DP index is equal to false, and then we would return false, right? So I think this should work, dude. Let's see if this submits. I think this should be good. Maybe not. Maybe it doesn't submit. Fuck. Okay, so we're gonna get another TLE. 79 out of 174. Are we missing something? I don't know. We're checking if it's inside here. If it's backtrack, we want to make DP index equal to true. Return true. I feel like we're caching here, but maybe... I don't know. Maybe... Anyone see why this is getting a TLE? I feel like this would probably... I don't know. I'm not sure. I would have thought I would have replied. Would have replied properly here, but I'm not sure. Oh yeah. I thought I'm applying DP properly here, but too many recursive calls. If anyone knows what's wrong with my DP, I'd really appreciate the help. I would have thought this would be the right way to do it. So, could you show the question again? Oh yeah. Sorry, dude. My bad. Yeah, I'm doing 55 jump game. It's in the top 100 most liked problems. I solved it using a backtracking solution. I mean, I planned it out a little bit, but looking through using a for loop, keeping it inside range here, so we don't get a out of bounds error. Then we backtrack if it's true. I'm trying to think of a better way maybe to speed this up, but I'm not really the best at DP problems, to be honest. I think I'm actually kind of trash. I can't really do a I think it's called top-down DP. Is that where you use an array? Top-down, also known as because it's top-down and bottom-up. Bottom-up. That's top-down DP. Top-down DP also known as solves a problem by breaking it down into small overlapping subproblems and recursively solving them, storing the results to avoid redundant calculation. Bottom-up DP or tabulation. Okay, yeah. So I'm doing top-down. That's what I'm most comfortable with, but I struggle a lot with bottom up, with like tabulation stuff, which I think I should probably put a little bit more effort into that, but which I will, but I very much struggle with it. What I'm thinking here. So we get a -1, so this looks good. If it's in the DP, this is good. So it's suggesting for me here to do an early check. But will that speed it up enough to get us out of this? I don't really know. We got a true here, return true, DP false. So here we probably want to do... What's up, J Pro? How you doing, dude? Not sure, but I guess you have to pass the updated version of DP as well. Or we can't do that because of the question. The updated version of DP. I'm not sure what you mean by that, Day about the updated version of DP. I'm not sure. I think what I'm going to try here is maybe doing an early check here. Where... So they're telling me that early check to jump directly to or beyond. So we're adding the current index that we're at is greater than or equal to the length of nums -1. What's up, J Pro? How you doing, bro? How's your day been, dude? So they're saying here that we want to do an early check here. DP being sent as a parameter. I don't think we need to send DP as a parameter. I think it's fine being a global here because really we're checking it in each recursive call. We're checking, you know, we want to hold, you know, the updated version here, and the updated version is always going to be outside here, right? Because it's not inside of our recursive call. So that's why I keep this outside. Because if I was to pass this in here, I believe if I was to pass in this hash map here into the DP function, it's not going to properly update within the recursive calls. So that's why I keep it outside. So we do an early check here, but why is greater than or equal to the length of nums -1? Or is there some sort of parent variable access issue? No. It's just I'm just getting a TLE redray, which means because of the constraints here, because we're looking at, you know, a number's length here up to 10 to the power of 4, that all these recursive calls here and me calling this min function and everything is too slow, you know, to pass the standards. And I can see probably why here, because they got a 39.5 acceptance rate, so that's probably a pretty good sign that there needs to be some like hardcore optimization done, which I am not the best at, but I can do basic top-down DP. So, but here they want us to look at the index value plus that index value. So I guess we're doing a little bit of an early call here is greater than the length of nums -1, right? Oh, wait, what am I doing here? I want to keep that, right? Is greater than the length of nums -1. Why am I changing that? Okay, if it is greater, then I assume here we'd probably just make DP index equal to false, and we would return, I guess, just return false, right? Oh, I know, we want to return false. Sorry, we would return true because we're going outside of we made it to the end of the thing. So let's return true here. Let's see if this lets us pass a TLE or not. If not, dude, honestly, I might have to relook at the solution. Oh, no, we passed. Okay. So we are the slowest solution. So my way of doing it. So what is the optimal way? I assume it's probably some greedy approach. You take the length of the nums, last is equal to 0. For I in range n. For I in the range length of nums, they check if I is greater than last. If I is greater than last, you return false. Last is equal to last. I assume this is probably some bullshit here to make it run faster. Inshal, keep it up, bro. Thank you, dude. Appreciate that, man. Thanks for stopping by and dropping a message, dude. Thank you. Appreciate it. So I'm trying to understand kind of what he's doing here. So he's looping through the length of the numbers. Will actually increase your time complexity. Yeah, that's what I did think. I mean, I did know that, but what I'm trying to understand is the greedy approach that this guy did here. What the length of nums last is equal to 0 for I in range n. If his I is greater than the last, he returns false. So if it's greater than the thing, last is equal to max, last I plus 1. Let's look at something else, see what someone else did. Imagine you have a car, you have some distance to travel. Gasoline, you can keep traveling on this road. The array, every time you move up to one element in the array, we subtract 1 of the unit of gasoline. So, however, every time we find an amount of gasoline that is greater than our current amount, move up 1 element in the array, we subtract 1 unit of gasoline. However, every time we find an amount of gasoline that is greater than our current amount, we gas up our car by replacing our current amount of gasoline with this new amount. We keep repeating this process until we either run out of gasoline and return false, or we reach the end of it just enough gasoline or more to spare, in which we return true. Wow, that is such an interesting way to think about this problem. If gas is less than 0, we return false. Else if n is greater than gas. See, dude, I don't understand. Yeah, I'll show you my solution again, Ethan. Sorry. This is my solution. This is such an interesting way to think about this. I don't understand how someone can get this intuition and like solve the problem like this. Like, I don't understand how like people can. It's so impressive that like people can think like that. Like, it's just incredible. This is my solution. Just a simple backtracking approach with a for loop, and then I'm incrementing it by whatever index that we are looking at, and this min also keeps it in bounds. Just does NeetCode have a solution posted for this? I used to refer. Does NeetCode have a problem posted for this? I used to refer to his website a lot when I was practicing job interviews. The difficulty levels have gone insane. Yeah. He does have solutions on his website. I don't know if he has one for this one. I would assume he probably does, because this one's like probably an OG problem, so he probably does have one. Yeah, there you go. He does have a solution for this one. But he stopped making solutions, which kind of sucks, but because I used to look at them a lot too. You have to frame the problem in everyday context instead of just thinking about the code. Yeah, I agree. Maybe I'm just not at that level of thinking yet, Ethan, because I cannot think about it like that. Like, that greedy approach is crazy. Like, it's tough for me to think of a problem in like a greedy way. But anyway, let's jump to something else. That was a good problem though. I did like that. I'm happy I looked at that problem. I know folks who used to come up with such solutions. It's all about patterns lately. Yeah, it is. It's all about like focusing on the patterns and stuff. There's a jump game 2. Maybe we leave that for another day. I don't want to keep jumping. What haven't we done? We haven't done one of these. Let's take a look at this. Okay. Even n times n grid, where each cell can have one of the 3 values. 0 representing an empty cell, 1 representing a fresh orange, 2 representing a rotten orange. Every minute, any fresh orange that is 4 directionally adjacent to the rotten orange becomes rotten. Return the minimum number of minutes that must elapse until no cell has a fresh orange. Let's kind of zoom in on this a little bit here. So we're given 0 being an empty cell. So this is an empty cell. 1 being a fresh orange. We got 1 here. 2 being a rotten orange. Okay. Every minute, any fresh orange that is 4 directionally adjacent to a rotten orange becomes rotten. So the next minute, this one will come rotten, this one will come rotten. And then the next minute, this one, yep. Then it can only be this one, okay. And then this one. And really what we want to do is we just want to return the minimum number of minutes that must elapse until no cell has a fresh orange. This is impossible, return -1. So we need to keep track of the minutes. We need to keep track of till no cell has a fresh orange. Okay. So I mean, any sort of graph problem like this, I literally instantly think, I mean, it can be one of the two, either like a DFS or a BFS problem. In this case here, I'm probably just going to do a BFS because I feel like this is more suitable for a BFS because we're looking at a 4 directionally adjacent graph here. So really we can, you know, explore north, south, west, and east in one sitting. So probably import a DQ. Let me just do some basic stuff, getting the length of the grid. We want to take the length of the first column being 0 here. And what do we want to do here? Probably give it a 0, give it an m times n grid where each cell can have 1 of 3 values. So really what we want to do is we probably want to add every single cell that is rotten, I would think, right? That has a 2. Because if it's rotten, from any cell, we know that it's 1 minute, right? And then what do we want to do? We want to return the minimum number of minutes that must elapse until no cell has a fresh orange. The minimum number of minutes. But how would we know that how would we know for sure that every orange... How would we know until no cell has a fresh orange? How would we know that there is no fresh orange? When did I solve this? A little while ago. Oh, we got a new daily problem. Got the daily check-in. Might check that after this. So what I'm thinking here is... Hang on, if I was to... I mean, I feel like this is a pretty straightforward problem to think about. The only thing that I'm kind of confused about is how I would know that every orange is fresh. The orange in the bottom left corner of row 2 is never rotten. How would we know that it's not fresh? So really, let's draw this out. Really, I'm going to represent a rotten orange being red. And let's do yellow being the orange that's not, right? Okay. And then we have our green here being, oh, whoops. We have our green here being empty. So really what we want to do is, to begin with, is we want to loop over this grid and we want to add to the queue the ones that are rotten, right? In this case, in our first example here, we only have 1, right? Then when we go inside of our queue, right, we want to move 4 directionally adjacent, right? So in this case here, we're at the top left, so we can move up and down. And we want to make all of these rotten, right? So in the first iteration here, this is going to go run. This is going to go run. And then we're going to hold a time here, right? So in this case here, this would be times 0, right? So we'd be at times 0 here. Let's switch colors. This would be times 0. Now going here would be at time 1, right? Then we want to switch back. Then in our next iteration here, we're going to discover... Well, we were not even going to discover this because this is empty anyway. We're going to discover this one. We're going to discover this one, and we're going to assign it a time 2, meaning 2 minutes, right? Then we're going to, in our third iteration, we're going to discover this element here, being 3. And then what we're going to do is we're going to do our last iteration. We're going to discover this one being of time 4, right? And the way that we want to keep discovering this is that we want to just keep keeping track of these numbers, right? Using some sort of max value, right? And when we get to this element and we know that it's at a time of 4, we can return the max value being 4, which I believe is our answer. Our output is 4. So we can have some sort of max variable that's updating each time from each element that we're adding into this queue. And I think that's probably the way that we want to go about this problem. So for row and rows, for col and cols, we want to look at, okay, if the grid is, if grid row col is equal to what represents a rotten orange 2, right? We just want to simply add q.append. We want to append a tuple of our row and column. Remember that there is a case where an orange will never become rotten. There's a case where an orange may never become rotten. Where is that? What is it? What do you mean by the case where an orange will never become rotten? There is a case where the orange will never become rotten. The orange can never become rotten if it's not 4 directionally adjacent next to it, right? So are you saying that, you know, for example, I'm going to draw over this because I don't want to kind of redraw all this. Read example 2. Bottom left corner, row 2, column 2 is never rotted because rotting only happens, 4 directionally. Yeah. Okay. Yeah, so what you mean by that, Ethan, is that, you know, you can only go 4 directionally adjacent, right? Northwest, east, south, right? And so, for example, I'm going to draw over this one, but if this was empty here, we would never be able to get to this element here, right? Because this is not 4 directionally adjacent, right? We can't go diagonal. So therefore this one would stay not rotten. Yeah. I think that's right. Or the last sentence of the problem. Yeah. So probably want to loop through our queue here. And then we want to row call row call is equal to q.pop left. Oh shit. But we also want to add a time here, right? So adding our time being 0, right? We append here. We need to make a queue, right? And then we obviously need to make our directions array being a north, south, east, west. Yes, exactly. Maybe there is a way to early out with -1 if you detect an island orange. Okay. Way to early out with -1. North, south, east, west, right? So if we were to go north here, north would be 0, -1. Our south would be 0, +1. And our east would be What is our east? We're going back towards 0, so we would go -1, 0. And our west would be +1, 0. We hit our grid, while queue, row call. We check. What do we want to check here? Well, oh shit, we gotta pop our time though, so. Really the recursive part of this would be here, where we would go 4 directions. Sorry, 4 new row, new call, and directions. I want to pass our new row being our new row plus our current row, our new call being new call plus our current call. Then checking our bounds here. Do a simple bounds check. New rows less than rows, and zeros less than or equal to new calls less than calls. And obviously we need to check that this is a fresh orange, right? So we would check our grid new row, new call, sorry, is equal to 1, being a fresh orange, and as well that it's not invisited. And new row, new call, not invisited, right? And when it's not invisited, then we can simply append our new row, our new call. We also want to append to our visit array here, right? So we would go visited dot add, pass in our new row and our new call. Here we need to check, okay, well, we need to keep some sort of global variable up here. Now that I think about it, we need to define our visited set. We need to keep some sort of global variable being like, let's call it resmax is equal to 0, right? When we pop from here, we need to check, okay, well, if time is greater than max time, I guess we could just do a max here, low-key. Resmax is equal to the max of resmax and time, right? We get that. We loop in a 4-directional way. We check our bounds. We append visited. We append our queue. I believe that should be good, and we would just return our resmax. Return our resmax. Unexpected indent. We needed a range here. In our range rows. Our range calls. Oh shit. I got this. How did I do that? Not enough to unpack. Pack expected 3, you got 2. Okay, well, I forgot to add our time here. So now we want to go from our original time and we want to +1. Okay. Why is this not working here? So this looks right. If it's equal to 2, 1 being a fresh orange. We only want fresh oranges when we're looping, right? So if this is and new row, new call, not invisited. Oh, we got ands for everything. I think this has to be an OR, right? If 0 is less than or equal to new row. It should be ORs, not ands. I think that was an accident. Or. This index is out of range. Oh wait, no, we don't want it to be all. What am I doing? We want to know that this is inbound, so we need everything to be true, right? So if 0 is less than new rows, less than rows, but new call is less than calls, and grid new row new call is equal to 1, and new row new call not visited, we add 1 to our time. We return our res max. If our grid row call is equal to 2, we append our queue. What am I missing here? I feel like this looks good. What am I getting? Oh, this is a 4. So that's why we're not returning anything, because we need a way to get out of here. So we get our res max. We're not actually checking if something, because if we were to still print this, I mean we can't, but if we had a way to print this, we have no way of telling that this res max, it works for the cases where it found everything, but we don't have a case where it would return -1. And how would we implement that case? How would we implement the -1 case? How can we tell that how can we tell that we never got to, that we have an orange, a fresh orange still left over? I'm not sure, to be honest. I'm not sure how we can get that case. ATB, bro. I have no idea what ATB means. What does that mean, bro? All the best. Okay. Thank you, dude. Thank you, Div. Appreciate that, bro. How can we check this? Well, maybe in the beginning we can we somehow like maybe we can somehow count here or something. Else if grid row call is equal to 1. So if it's a fresh orange, then we can count. Fresh orange plus or equal to 1. We count our fresh oranges. If we find a fresh orange, which is what we do here, we can do fresh oranges minus or equal to 1. And we return res max if fresh oranges is equal to 0, else -1. I believe. Cannot actually look where fresh oranges. Wait a little bit. Nice. Okay. Good stuff. Let's take a look at our daily problem. Just refreshed. I should probably save this for tomorrow. kind of want to solve this tomorrow, probably. I won't do that today. I'll solve that tomorrow. Shit, not this page. Maybe we can jump through. Let's try and do one like easy problem or something. See what we can find. Longest common prefix. I wonder how many easy problems there are, bro. There's probably so many. Lucky numbers in a matrix. Because I'm lucky. Let's take a look at some lucky numbers. Given m times n matrix, given distinct numbers, return all lucky numbers in the matrix in any order. A lucky number is an element of the matrix such that it is the minimum element in its row and maximum in its column. Okay. So I think we do this. We go rows is equal to the length of rows. Cols is equal to the length of cols. Oh, the length of, not rows, matrix. Then we would go cols 0. What do we do here? Okay, so we probably want to. So what are we returning here? We're returning a list. 15 is the only lucky number since it is the minimum in its row and the maximum in its column. Okay. I thought it was going to be the maximum in both. A lucky number is an element of the matrix such that it's a minimum element in its row and a maximum in its column. Oh. So how do we want to do this? What is the best way to go about this? For row in rows, row in range rows, for col in range cols. Let's do our matrix. Oop, this is meant to be matrix here. Matrix row col. Let's print this. Okay. Would be the best way to do this, maybe flatten all the rows and loop through them. Are they unique here though? That's the question. Find out and save the minimum of each row and make column in each two lists. Then scan through the whole matrix to identify the elements that satisfy the criteria. And 50, 10 to verify. Finally we got out of the forest piece. That's funny. What was that one here? Well, find out and save the minimum of each row and maximum of each column in two lists. Find out and save the minimum of each row, the maximum of each column. And scan through the whole matrix to identify the elements that satisfy the criteria. Okay, so I feel like we probably have to do maybe some like list comprehension here. And I always forget how to do it. Always forget how to do it. Expression for item in iterable if condition. Call list. Expression for item in iterable. Matrix of distinct numbers. Shit, I didn't see that. Okay, distinct numbers. Return all lucky numbers in the matrix so there's no duplicates. Lucky number is an element of the matrix, so it is the minimum element in its row and the maximum in its column. In row. Row in matrix. What is the min function here? For call in matrix. That's not going to work though for that one. How would I find the column one? How to find minimum in column. I actually don't know. A minimum in a column. I know we're looking for the max here. Whoops. We're looking for the max. Call for call in saying zip matrix. Well, what does this do? What does this star do in Python? What is star matrix? It transposes the matrix, that is, converts rows into columns. Oh shit, I didn't know it did that. No, Ethan, I'm gonna do it right after this. This is gonna be my last problem, and then I'm gonna work on it. I'm gonna make some food and work on it. I'll probably call you around like, I don't know, probably around 9 or something. Probably an hour and a half. Unpacks the rows like pairs elements by index 1 force. Oh shit. I didn't know this transposes the matrix in Python. How did I did not know about that. Transposes the matrix in Python. Shit, I didn't know it did that. Okay. So then we zip all of them together as elements by index. Wow. I didn't know you could do that in Python. That's interesting. Okay. Okay, so let's print our row list just to visualize it. Print our call list. Let's print our call list here. Rows is not defined. Oh, whoops. Let's get rid of this. Okay, so this is our row. This is our column. Interesting. Obviously, we're gonna need a res. Row in matrix. Colon row. We want to check. We want to get the max. What do we want to do? A lucky number is an element of matrix, as it is the minimum element in its row and the maximum in its column. So we would do let's do another call for num. If num if num in row list and num in call list, and we want to res.append. Oh shit. Res.append our well, if it's in both, we can append either. I mean, append num, and we return our res. I think that should work. Okay, there we go. Let's see some other ways we can do it. Okay, so this guy did the same thing. JVal, you're right. If so interesting. I did not know you could do this in Python. That's so cool. You can transpose it using columns. That's crazy. Like probably this code in like C++. It's let's see. Yeah, dude. Like you look at this, dude, and you fucking do it in Python. Oh shit, he did it this way. Okay. He was doing it the original way I was thinking about it. So where you go for iron regen, you'd get the min, you'd find the min, then you get the max, the rows. Sorry, this is columns, this is rows. You get the min in the rows, you get the max in the columns, create your lucky numbers array, then you'd loop through everything and you'd check if your I and your J is equal to the minimum of row I and the minimum of col max. If it is, then you'd append and add it to your lucky numbers. Yeah, there isn't a linear algebra library in C, C++. Yeah. Let's have a look at the C++. Yeah, bro. You look at this solution, and you look at like... This is so interesting that you can do this. Like, the only way I would have... Yeah, like the only normal way is probably thinking of it like this. But then you're having like... This is crazy. Crazy stuff. Look at that, dude. This brute force solution got a proof of uniqueness. This is crazy. Like, why is lucky numbers wrong? Jeez, man, what a detailed solution this guy has. My gosh, this is insane. C++ is doing it in the same way as the other manual Python solution. Yeah, I noticed that. Let's have a look at it again. Where is the C++? Yeah, Roman getting the max. What is Roman? Pushing it to a vector. Okay, array. Ping through, pushing it. Like, Ethan, you couldn't do You couldn't do any one-liners like this in C++, right? Like, this stuff does not exist in C++. You gotta do it the manual way, man. This is so interesting. Like, anyway. I don't understand the solution, but I drove a comment. Can you give one line explanation? Cool. All right, I'm gonna call it there. Not in the std stl. You can implement it yourself by overloading your operators. Oh, okay. All right. All right. Well, I think I'm gonna call it for today. I appreciate everyone that watched and sent some messages. Thank you guys. I will see you guys tomorrow, probably around the same time, like 6 p.m. Central. So, yep. Thank you guys, and happy day 150.